and we are Group 5 presenting Chapter 5. My name is Kay. I'm a machine learning engineer here in the Bay Area. Ern, if you go to the previous slide, I think we have on the list of the team members. Yeah. So I'll let the other team members introduce themselves. Sachin?
Hey everyone, this is Sachin and I am a lead data scientist at Target. I'm based out of Bangalore.
Yeah, hi, hello everyone. I'm Rohan Singh Rajput. I'm senior machine learning engineer at Headspace. I'm based in Los Angeles, California.
Hi, this is Ola. I'm also an ML engineer at Tim Hortons, and I'm also previously intern at Yoshi's Lab. Thank you.
All right. I think the other team member isn't able to make it today. And we're going to go over the different sections of Chapter 5. Today may not be in full detail, but basically go over the sections and talk about our experiences and what we think about or what we learned from the chapter or reflect on it and so on. All right, next slide, please. So I'll go over introduction and some pre-processing techniques, and then my teammates will cover the rest of the topics. Next slide, please. All right, so starting from the basics, what's a feature? So you can think of a feature as either that's something that's learned by the model automatically, a representation of the data that's fed to it, or something that you manually calculate based on the raw data that you encounter. So if you think of a neural network and you're doing an image classification task, and you feed pictures of dogs or cats to the model, and it learns some features from it, and you have a label for every data, and then do all the convolution and backpropagation. And the model learns some representation of the data, and then it learns to classify between the two or however many classes that you have. On the other hand, if you think about it as a tabular data format, for example, for every sample, you have length of the whiskers, color of the nose, length of the face, and things like that, different feature of different characteristics of the sample. Then you can think of, okay, what about if I calculate the median length of whiskers and use that as an input? So that would be something that you've calculated manually. It's engineered from the data. That's a feature that you've calculated. So you can think of features as these two types. Now, the rest of the chapter, you can assume that mostly applies to non-neural network type of models because in neural networks, you usually associate the model to pick up on the features on its own. And calculating the features from the data, engineering it is considered an art by many because over the years you build up some experience. It might require some domain knowledge as well, depending on which domain you're operating in. For example, if you're doing something related to cancer research or biological field, then you might want to, get input from subject matter experts to craft interesting features that get the most value of the data. So that's why it's considered an art by some people. Next slide, please. Why is it important? Other than having a rich source of data, a lot of data for all the classes that you're trying to learn, using the model, the next best thing that you can do to get a performance boost out of your setup is using feature engineering. Now, you might have whatever the state-of-the-art model is, lots of data, and you have established a baseline, and you want to improve on that further. You want to extract as much value as possible. Then one of the ways to do it is through feature engineering. You might want to see, okay, what nuanced topic that I can extract out of the data? What else can I provide to the model that will help it classify the data even more. So you can think of it as, if you present this particular set of data to a subject matter expert, how would that person classify between the different samples? So what are the things that they look at? So you can you can follow that logic and come up with different features that you can use to enhance your training pipeline. And this is one of the ways that you can get a lot of performance boost other than hyperparameter tuning, which involves a lot of effort as well. So from my experience, I found that once you have established a baseline, thinking about what other features you can come up with is one of the best ways to use your resources if you are looking to improve your performance. Next slide, please. And when you think of engineering the features, some of the things to keep in mind are you cannot directly use raw data as is and hope that the features that you're building will enhance your performance. There are some pitfalls that you need to be aware of. For example, one of them is the scaling issue. So going back to the previous example, let's say you had some of the data in centimeters for the whisker length of the cat, let's say, and some of the data was in inches. And if you do not account for it and train the model without accounting for this, then you might run into issues, because the model might think the higher the value of the number, more important it is. But if you convert all the numbers to the exact same unit, it might mean something else. So you have to be aware of that when you're handling the data. And sometimes you're not given full data, or sometimes it's not possible to access full data. There's some rows missing. And although there are ways that the model can intelligently handle it, depending on which model you're working with, sometimes it's better to handle that manually. And also, sometimes if the data is missing, then that might mean that's an information in and of itself. Maybe you don't want to fill it with some random data. And also, when you're filling it with some, let's say, median or mean value of the entire column in the missing rows, you might want to be careful doing that, because if you're using the entire population to come up with the statistic that you're using to fill the missing values, then you might be snooping on the data, which is also called data leakage, and we'll talk about that more. We'll talk more about that later. So inadvertently, you're using information from the test set into the training part, which would lead to unrealistic performance expectations, because the model is seeing, or kind of cheating, because it already knows a little bit about what it's supposed to predict while it's training, which will not be the case when you're implementing the model in the wild. When it's in production, it cannot cheat. But if you allow it to cheat when training, you're setting it up to fail. And one of the things from my experience, I'd say that the other thing that you need to be careful about is what kind of access do you have when performing these pre-processing techniques. For example, if you're implementing a model that is supposed to be only using the data that's available to it at the time of inference, you should also be accounting for that fact when training the model as well. You have to be careful, okay, what parts of the population I can access during inference. I should be only accessing that parts during the training as well. And the other minor point is the discretization. It's also called bucketization. And in my experience, I haven't used this technique a lot. So it's basically, if you have a wide range of data for a particular variable, then you would want to set it up into different buckets. Let's say the value can take value number between 0 to 100,000. Then you make it into 10 different buckets from 0 to 10,000, 10,001 to 20,000, and so on. And then fill in the values in those buckets. This is not often done, but that's something you can look at as well as a pre-processing technique before engineering the features. From the next part, I think Ola is going to continue.
Yep. So I'm going to talk about encoding categorical features. So like when you have categories in your data, you want to map them to numerical values. And oftentimes we have static features, like we have probably things like age bracket, or income value, things you don't expect to change, features you don't expect to change when your model is in production. But there's some specific cases where we have categorical features that actually change, like in the case of building a recommendation system. Say you have a list of products that you train your model on, and of course, when you train your model, those kind of models you train on your, like within the window period, so the past 1 month to the past 2 months. So what happens when the product is being what happens when a user encounters a product that wasn't in the training set, that wasn't in the mapper, in case you kind of generated a mapper. So it's going to throw this kind of like that means your model was not that means your model has not encountered that product. So what do you do in that kind of specific scenario? And so here the suggestion is to make use of things like hash and shrink. And I was also experienced this problem in my previous role at Tim Hortons, where I had to kind of use well, we have this kind of list of products we train our model on within the past 1 month. And when a user comes and they encounter and they request a product, or we encounter a product that our model didn't see during the training period, like the past 1 month, say, and hold product, like maybe a product that maybe the last time it was purchased was like 3 months ago or 4 months ago, like out of the window period of the training set. So what happens? Do you just recommend some default items, or do you make use of some kind of a mapper that you save in a DynamoDB that can or do you do some kind of sanity check before you pass the input into your model? And so these are some of the things like we face, like that you might have also faced also. So the idea is to use an hashing trick, to use an hashing function, sorry, to use an hashing function that can map your categorical values to a number. But when you talk of hashing function, you start thinking of collision. So you can start thinking of the possibility of mapping the same categories to the same hash value, to the same hash token. And so what we do is to make sure we have this kind of course, it's a simple hash function will be the modulus operation, right? Where you have your whatever parameter modulus, kind of a fixed number, then you generate this kind of a kind of value that can expect to be unique across all your brand or your products. And so the choice of hashing functionality is also something you have to pay particular attention to. And so next I'll jump to feature crossing. And feature crossing is where you kind of bring two features together, where you kind of combine two features together to generate a new feature. And the goal here is to learn non-linear relationships in your data. And but the disadvantage here is that your feature space can blow up. So you're gonna have more features than than expected. And sometimes it can make your model to overfit to your training set, to your training set, which is not what you want. And of course, another thing you should keep in mind when you're generating features is to talk about positioning embeddings. And this is something you're probably familiar with if you've read the paper on transformers. And so the goal here is to encode the position of your token in your input data. And especially when we do things like when the sequence of input when the sequence is kind of important, like in things like machine translation, or like mostly in language modeling tasks. And so there are two approaches that was stated in the book. One is to use dynamic embeddings, just similar to the way of what embeddings, where you can actually learn the embedding matrix for the position kind of for the positions of the tokens. And the other way is to use fixed embeddings, like when you use sine and cosine, that's trigonometric functions, to kind of uniquely identify the position of the tokens. across your input representation. And so next slide. Then I'll talk here about data leakage. So data leakage is when you use when there's a leakage across your test and training data sets, and this affects the performance of your model. This makes your model not to kind of generalize to the test case. So, and of course, you're training wrongly when you allow data leakage. So the first scenario is when you have time correlated data. The default way in machine learning is to split your data randomly for it to generate the training set, the depth set, the training set, the depth set, and the test set, right? But then when you have the data that is time correlated, an example is when you have maybe time series data or whatever, you want to make sure you split along the time dimension, not just randomly, because splitting randomly will leak like we kind of make you to we will not make the model to learn the underlying structure in your data, because then you're mixing like across the train and the test set, right? So one way is for us to make sure you split along the time dimension and not just randomly when you realize that your data is time correlated. And another instance here, another scenario is when you have to apply global statistics of your data to both the training set and the test set. And so literally you're looking, so you have a data and you've calculated the global statistics, the mean, the variance. You want to do scaling, for instance, and you've calculated the global mean, the mean across the entire data, both the training set and the test set. And so applying that to the training set is leaking information from the test set, which is the wrong way to do it, right? So we want to make sure you're applying your data statistics the right way. You compute your statistics for the training set separately and the one for the test set separately. So to make sure you're not leaking you're not leaking like information across the train and the test set. Then another case is when you want to do imputation. Say you have missing values, and you want to impute your missing values with the mean with the mean or the median of your data. You want to make sure you're not using the global statistics. Otherwise you'll be leaking info across the test set. Then another case is when you're handling duplicates. And so you make sure you want, and I think I put a good summary here. One is to split before scale and to impute and handle duplicate before you split your data sets. And I'm going to quickly talk about the last one, which is the leakage from the data generation process. So there's some data generation process that kind of lead to data leakage. And one thing you want to do is to make sure you understand the process of with the process that generated the data. An example in the book was given about CT scan. Okay, I think because my time is up, I'll just move to the next person now.
Yeah. So you all might be wondering, right, why we have data leakage in this chapter. So because after all, this chapter is for feature engineering, right? At least I thought about it when I was reading the book, and seems that the reason is that feature engineering and data leakage are related, and that is we need to engineer good features, but we also want to ensure we aren't causing data leakage in that process, right? So till now we have talked about all the good parts of feature engineering and why we would want to do feature engineering. Let's talk about the other side, right? If you go for feature engineering, like you overdo it, you can cause data leakage because of mismanagement of data, right? It can also cause overfitting, which is like you might start modeling noise. Of course, you might have tech debt and higher inference latency because your model size can be bigger, right? So what you would want to do is you would want to follow Occam's razor here, right? Which says that simpler model with similar performance is always better, right? And feature engineering and adding more and more features to your model adds to complexity of the model, right? Now, like we also wanted to bring in the latest models, right? So and there's a lot of question about whether feature engineering is dying because of neural networks, right? Because neural networks are doing some bit of feature engineering by themselves. Right. But if you take some of the examples from the state of the art neural network models, for example, DCN from recommendation models, it explicitly uses feature crossing. And I think Ola talked about feature crossing in one of the ways of feature engineering, right? Lastly, I just wanted to talk about like how I engineer hour of the day as a feature into my model, right? So the main nuance there is that if you keep it as a continuous variable, you would like have the 0th hour, first hour, and similarly till 23rd hour. But then you are not able to capture that 0th hour and 23rd hour actually are very close. However, in the numerical space, they are not, right? So looking at cyclical features like cyclical encoding, which will like give you sign and cos like features, will give you a bump in performance. And I've like actually seen it in my like work, right? Can we move to the next slide? Yeah. So so while you are engineering new features, right, you would want to know which feature is good, which is not, and that is where the feature importance comes into play. And you can find out feature importance from some of the built-in methods from, for example, libraries like XGBoost, Random Forest have their built-in feature importance methods. However, they have some flaws, right? So for example, if you have a feature which has high cardinality, uh, basically it has it has a lot of levels, right? uh, it might favor those kind of features in terms of importance. And another flaw is that basically you are all the feature importance you are calculating it is on the training data. However, you would want to like it's not your feature importance might not be generalizable, right, if you're doing all on the training data. So maybe you would want to look at permutation feature importance, which kind of solves for both these flaws. And it is an interesting concept where like you permute the values of the features and you see what is the impact on your model performance. And that is, I think, also one of the statements which we have in the book, right? That feature importance is the effect which you can calculate of the feature if it is not there in the model, and what is the effect of the performance, right? Then there are other methods which are more model agnostic methods, right? Like SHAP and LIME, right? One additional benefit you will get by using these methods will be you can get feature importance at a data point level. So it will add to interpretability. So let's say from the business perspective, you want to, the business is looking for why this data point was classified in a particular way. You can add to interpretability by looking at SHAP and LIME. Finally, when we talk about feature generalization, right, you would want to look at feature coverage and distribution. So by coverage, we mean that what is the percentage of missing values in your feature. You don't want a lot of missing values in your feature, right? The second is the distribution, right? So the feature distribution has to be same in your training data and your testing data. You don't want the distribution to change, right? And that is somewhat related with the coming chapters where we talk about data shift, etc. Let's move to the next slide. Yeah, as a summary, overall, what we want to summarize is that feature engineering for sure can boost your performance of your model, and it is one of the top methods for improving performance. You can like you have to have some pre-processing methods initially, right? And feature importance can give valuable insights for your model. When basically, if you want to look at it from a selling point of view, sometimes as data scientists we have to sell the model to the business, so feature importance can come in handy there, right? Ultimately, what we want to say is that neural networks are good at feature engineering, right? But it is always a good idea to engineer features from domain knowledge, so that will save training time, model size, and complexity. We talked about it. Yeah, I'll just hand over to Rohan for the next part.
Thank you, Sachin. So I will be sharing my screen for the discussion section. Please let me know if you can see my screen.
Yeah, we can see it. Thanks.
Yep.
Yes.
Yep. So yeah, in the discussion section, as our group name suggests, we are like a recommendation system expert. So we'll be talking about the next area of recommendation system, where how can we leverage generative AI technology in many ways, like enhancing the recommendation system, or in a one way we can also use generative AI to enhance our feature engineering pipeline. So in this section, I will be talking about like how we can utilize various types of generative AI, like large language model or stable diffusion, to improve like the recommendation system, or maybe like leapfrog the current recommendation systems we have. So very quick, like what is a recommendation system? I think you all know what is a recommendation system. It's an information filtering system which help us in decision-making process. It's a very prevalent field of machine learning. Like it's available in many products like Amazon, Netflix, Spotify, Google News. And there are like broadly three types of recommendation systems. One we say is collaborative filtering, in which we use like historical data of user and item interaction, and we utilize user similarity score. So for example, like we have a user A who likes like item A or item 1, and then there is another user B, who likes item 2, and then if we find that like a user A also like like the item 3, and A and B are similar user, then we recommend this item 3 to user A. So this is like collaborative filtering. Similarly, we have content-based filtering. This method is actually helpful when we have like cold start problem, when we don't have like lots of user interaction data or like user history data, where what we can do, like we find a user who likes like an item 1, and we try to find like what are the similar items like item 1 using like item features, and based on that, like we recommend the similar item to user. And then we have a hybrid system that uses both of these mechanisms in the recommendation system. So this is how the traditional recommendation system look like. It is one of the type of recommendation system popularized by YouTube. Is called multi-stage recommendation system, which has like two important stages. One is called candidate generation, which actually takes a corpus of large number of items and filter it down to the few hundred items. And then once we get those few hundred items, we rank them, and then it's collect like few dozen for that can fit on our YouTube screen or like any of the device screen we have, and recommend those items to us. So this is how like our traditional recommendation system used to look like, where we had like a static deterministic corpus of content where we can like recommend to our user what is available inside our like content library. And this is how like generative system works. So the generative AI system works in a new paradigm way, where they can recommend as something like which does not exist in even in our like content database, or it can like generates its own information. So one example we can take in ChatGPT, where you can actually ask some prompting question like recommend some action movies to me, and the ChatGPT can like prompt you out like some of the movies based on popular action, and then you can ask like which one has the highest rating, and based on that it can do its own analysis and give you like which movie has like the highest rating among the recommended movie. Similarly, we can generate like any kind of picture or images using the prompting technique in stable diffusion model, which can generate a new image for us based on the style we asked for it. We can also augment the existing image, like we have like certain kind of image, and then we can change the image attribute, like change the color of this t-shirt, or maybe create a new kind of like we can do like style transfer, where we have like one type of images and then it can turn into another type of images. So all this like generation from this system can be treated as like new can be added to our content library, and can give like on-demand content recommendation to our user. So this is how one of the GenRec architecture proposed in one of the paper, and this paper name is like generative recommendation, where we have this like traditional recommendation. We have item corpus, we have like a ranking stage, and then we recommend to user, but the user has choice to get like recommendation directly from an AI generator, right? So user can actually like write some kind of give any kind of like query to the system, or we can understand from the user interaction history that what user is seeking for. And if that item is not available in our item corpus, our AI generator can generate like a content for a user and like give direct recommendation to user. Now, obviously, such system has like both pros and cons. So when we talk about pros, right, these are like, next generation system that can, create a personalized content generation, which, create a tailored content for individual preferences. It can overcome limitation of our like, content library. We can integrate user instructions. So rather than relying on like, lexical search query where like you just mention that what you want, you can actually be more like, implicit, and like, you can like write a semantic query where you can describe your situation. Based on that situation, system can generate or like, fetch the content for you. There is a versatility and trustworthiness where a system can also like, uh, authenticate and generate some kind of legal content within your realm. Now, the cons are like obviously the complexity. These systems have like lots of nuances, and these are like the previous systems are more deterministic system where we know that what type of content we have the library, and that is the only will be served to user. But the new system will require like, lots of processing to understand whether it matches the user expectation or not. Again, the questions about reliability, that the quality is good or not. There are lots of ethical concern because there will be some like, misinformation can be generated by an AI system, and there could be like some inherent like, biases, hallucination, copyright issues. And also one of the biggest issue can here like is the computation requirement, right? So because Gen AI system required huge amount of computation, and their latency might not be as within the SLA what we get like in the deterministic recommendation system. So there could be like, to overcome some of this issue, like we can actually introduce some of the guardrails here, right? We can like to overcome the hallucination, like we can have like a RAG-based system that can actually restrict the content to the content-based library and incorporate the facts and knowledge of the world. So this is our like, like the previous system, but if we add like another layer which actually has like, this fact and knowledge about the world, and it restricts our system to just only retrieve the content we are expecting it to retrieve, that actually help us to like, overcome some of the problem what we described previously. So there are like some of the application of GenRec we can see from the stable diffusion. So for example, like suppose we have like certain kind of input in our item corpus, right? And we have like 3 type of users who have like, different type of requirement. So there is a user who likes like, artistic work. So for that particular user, we can generate like an artistic based recommendation. Another user like, funny video. The same picture can be, turned into funny picture or funny video, or the another user like, cartoon style output, and that user get like an cartoon style output. Just imagine like, someone wants to watch a real movie, and someone wants to want an animated movie, and with the same movie, or recommendation system can like, create 2 movies for 2 users, and both can like enjoy those kind of movies. Again, like we have like, different types of like, videos available, and based on that, a user like, historically this kind of a costume. So the AI can generate like, different thumbnails for different users on like, YouTube videos or like any other platform. Another thing is like, how we can integrate like, LLM systems in our recommendations. So previously we saw like how stable diffusion can help us. Here we will see like how ChatGPT, Bard, or Llama kind of system can help us to in our recommendation system. So this is one of the system described which uses like LLM like architecture. So as we can see that we have like, in one column, we have like this prediction task where we are like, predicting some kind of movie rating based on the user prompt. So suppose like the user currently watched like 5 movies, and then based on that, we have like a top 5 recommendation. Again, we have like a rating prediction where we have like several ratings of movie available, and the user can like, prompt that the system, and it can generate like a new rating. Again, like in the generative task, a system can actually ask several list of questions to us and then recommend us, like, what do you actually like. It can ask like a very explicit question that, like, if you are looking for some kind of movie and what you have watched in historically, and based on that, like, it can give you some kind of explainability of that recommendation, and also provide you like correct answer. So this system is called P5. It is one of the system developed by this team. It's also called as RLP system. It's based on like transformer T5 system, where we have like several type of tasks given to a sequence based recommendation system, and based on like type of task you give to the system is generating various type of output. The first time, like if it is a sequential recommendation, it is generating a sequence output. Then you can ask a rating prediction question and it will generate a rating for the output. And similarly, if you ask for explanation, review, summary, direct recommendation, it can do all the kind of work, and it can do all the type of multitasking we required for a system. Again, like I will skip this section just for the time being. Just it is saying that, like, what we can do, we can not only do like the pairwise selection prompting, like whether this movie is good for you, yes or no. We can also do like ranking wise prompting, that which particular recommendation, you can generate like an order list, like this is the top 5 movie I'm recommending you, rather than just giving you like one single movie. Again, there are like various issues in this kind of system. Obviously, there are like fairness and bias issue can generate in this in this kind of system, specifically like some of the sensitive areas like education, criminology, finance, and healthcare, where like there is a lots of like historical bias available in the data set. And to overcome that, like suppose like if we integrate this system in Amazon, and Amazon is generating like recommendation with hallucinated and like unavailable features as a like feature, like a item description, that could be like a misleading advertisement, and user might buy it because LLM is trying to like sell this product at like high rate, and that is in the objective of recommendation system. So there are like we have to make sure that like we make sure the data we are feeding in this system should be as unbiased as possible. We do like all the like checks, compliances, to make sure that like it's meeting all the like fairness audit, do like third party audits, feedback loop, all kind of this legal and ethical requirement, like we should be doing before launching this production, like before launching this product in production. Yeah, so that's how like there are like lots of, as I discussed, like there can be several things we can do to assess the fairness of this recommendation system. We can do third-party audit, community involvement, like Twitter doing it right now with like some kind of community notes, and we can educate our user more about like the fairness metrics and get like some kind of feedback mechanism, so we can get feedback from our user. So with that, I will conclude this presentation, and these are some of the questions we kept for the discussion in our break room. So yeah, what are the tools you are using in company to build like feature store? How can a GenAI LLM system can be used in feature engineering? What are the difference between online and offline feature stores? Which is more challenging to build, maintain, and monitor? At the last, what kind of ethical guidelines should we have in place to responsibly collect user features? With that, I conclude my presentation.
All right, thanks, Rohan. Thanks, Group 5. Yeah, I apologize for the beginning technical issues with the echo. But right now we're going to break out into the discussion groups, and then I'll end the stream for the YouTube viewers. So thanks for joining and staying on through the whole presentation. Thanks a lot.